Hi, my name is Amanda,
And I'm Hans.
and our company, Big FDM Printing, is the leading company in industrial FDM printing. This project is looking to break BFDMP into new markets with isotropic, economic, and functional 3D printed parts. FDM printing, FDM printed parts display weaker inner layer bonding, which leads to a worse mechanical performance in the transverse direction. This limits FDM applications in lightweight, high-strength industries like aerospace, automotive, and medical devices. This project seeks to boost the mechanical strength of FDM printed products in the transverse direction by modifying an FDM printer to incorporate silicon carbide fibers between the layers.
We know that silicon carbide has been used in many polymer composites to increase strength. Additionally, FDM, as we're well aware, is very quick and very easy when compared to other 3D printing techniques. However, FDM parts also often result in anisotropic parts, which are up to 3 times weaker in the transverse direction. This is one of FDM's major flaws. We also know that a dual extrusion printer are capable of printing 2 materials at once. We propose that incorporating silicon carbide fibers into the FDM printed parts will increase the tensile strength in the transverse direction between the layers. A dual extrusion head could insert short silicon carbide fibers in between layers without greatly increasing the production time. Isotropic FDM printed components could expand the company's scope to new markets. Here is a full diagram of our proposed 3D printed composite apparatus. To start, we have our dual extrusion head with one head for printing the silicon carbide fibers and another head for printing the polymer filament. Initially, this heated polymer filament head will lay down the first layer of polymer. Then, this layer will completely cool, and next, the same apparatus with a different heated head will come around the same layer and insert these silicon carbide fibers with the heated head, which will continuously melt the previous layer and heat the silicon carbide fiber while continuously moving along the layer. It will insert the fiber, and as it is moving, it will cut with these scissors here the correct length so that these silicon carbide fibers are the same width as the polymer layer. This allows them to simultaneously be inserted into the first and second layer so that these will alternate printing so that one layer is polymer and then the next it'll print these silicon carbide fibers and then it'll come back around and print the next layer with fiber. This will result in a fiber aspect ratio where one layer of polymer is over the diameter of the fiber. This new composite printing technique will positively impact BFDMP by allowing us to branch into new key industries, such as the automotive industry, where durable parts for vehicles are in especially high demand. Additionally, the medical industry requires biocompatible components for devices such as prosthetics and dental implants. Also, for the aerospace industry, FDM has already been proven useful in Airbus components, and perhaps introducing isotropic and high strength materials could expand the possible applications. The demand for strong isotropic materials in these industries means that customers are willing to pay more for highly specialized components than for typical FDM parts. This new technique would shift the focus of the FDM market away from prototyping and actually towards functional parts.
On to the main equipment and materials, we plan on beginning an external partnership with Raise 3D. Raise 3D has a dual extruder printer which is able to intake and to print with 2 different filament materials at one time. Through our partnership with Raise 3D, we plan on modifying the extrusion head to be capable of both polymer and silicon carbide deposition. Raise 3D will be able to assist us with determining how to modify the software and the hardware components. One head will remain as is for standard polymer deposition with filaments like PLA, ABS, and more. And the second head will be fitted to extrude silicon carbide fibers into the polymer layer and will have scissors to cut the continuous silicon carbide fibers. At the materials that we will use are twofold. Starting off, we will continue to use just standard filament like PLA, ABS, or PETG. The other material we will use is silicon carbide fibers. These will have to be high strength and high temperature resistant. There are several different aspects that are worth considering. One of the aspects is the diameter. A smaller diameter, like 75 micron, correlates with a higher tensile strength and higher stress transfer between the matrix and the fibers. However, the smaller diameter may be harder to handle and accurately insert into the polymer layer. So we may want instead a thicker diameter like the 142 micron thing instead. To combat the difficulty to handle, we may also want to bundle the fibers together. With any new project comes a litany of risks. Several internal risks that we're facing are technical challenges and timeline delays. There are many possible technical challenges that we'll come against, but the main ones are getting consistent fiber alignment and adhesion with the polymer. The timeline delays are that prototyping, testing, or even achieving consistency may take a lot longer than expected, which would delay milestones. So we need to put some guardrails and contingencies in place so that this doesn't happen. Some technical guardrails include conducting extensive testing and optimization during the creation of the printhead itself. Along with this, we need to ensure there is a diverse engineering team to provide a variety of perspectives and account for blind spots. We also need to ensure that there's buffer time built into the project timeline to account for delays. To ensure that the production of this new printing technique goes as smoothly as possible, as mentioned before, we are partnering with Raise 3D for technical support, resources, and troubleshooting. It's worth mentioning that if Raise 3D ceases operations, this would be a potential kill criteria for the project, unless, of course, the team members have gained adequate experience with the machinery. The biggest challenge that we're having with this new composite printing method is the impact on printing speed. It's projected that the printing speed will increase about 3 times due to the additional steps for fiber placement, alignment, and cutting. However, we have some mitigation strategies that will help to reduce this time. Firstly, by synchronizing the second extruder head with the first, it will help reduce time required for fiber insertion, cutting, and even the time used between them. Additionally, new software will be developed to minimize the gaps between the two extruder heads, which will shorten delays between polymer and fiber deposition. It's also worth noting that the customers in these specialized industries are much more interested in superior mechanical properties and are willing to accept longer print times. Additionally, the increased production value from the higher isotropic strength and durability will offset the slower production.
There are some other challenges that need to be taken into consideration, such as how will the fibers be added into the cooled layers? The second extrusion head will be heated in order to remelt the previous polymer layer as the silicon carbide fibers are inserted into the material. Therefore, the layer will be soft enough for the fibers to penetrate and bond to the previous layer. The fibers themselves will also be heated, which allows them to enter the layer and bond more effectively. You may wonder how the system will be able to handle the increased complexity of the printing process. A major component of this project is customizing the software and customizing the hardware in order to ensure precise timing and coordination between the polymer extrusion head and the fiber extrusion head. We can optimize the print path of each component to ensure that the fibers are placed in the correct areas and avoiding areas such as the polymer wall. We will maintain consistent fiber alignment even in complex parts by utilizing the precise rolling mechanism displayed in the original diagram, as well as a real-time monitoring system implemented into the modified extrusion head. I'm going to discuss existing technology and the state-of-the-art of increasing the tensile strength of 3D printed parts. Firstly, FDM printed parts can be improved by increasing the print head temperature, decreasing the layer heights, or slowing the printer speed. While this can increase FDM tensile strength in a significant way, it eventually reaches a point where FDM strength reaches a limit and other techniques are needed to increase the tensile strength. One of these techniques is by 3D printing composites. This can involve laying down a continuous carbon or glass fiber between layers, as shown over here in this diagram where the filament is being laid and the polymer is being laid right on top of it. Additionally, chopped fibers can be introduced into the polymer matrix as seen here, which can increase the structural integrity of the filament itself. Lastly, continuous fiber can be inserted into the polymer layer by achieving similar effect to this, but with better binding to the layer. Finally, the main competitor to our proposed idea is selective laser sintering, which is a technique which can produce complex and isotropic parts. However, this comes with a higher upfront cost and a higher cost of operation. Additionally, it results in the similar surface finish issues as FDM, but with a slower printing speed.
After some cost analysis, we are requesting $375,000 over the course of 2 years. The materials are projected to cost $20,000. Our service contract with Raise 3D will cost around $30,000 a year. We currently don't have any space, and so looking for new lab space will cost $50,000 in capital. Our energy will be about $1,000 a year, and our overhead will cost $130,000. This project will result in a printer which is exclusive to BFDMP and whose products cannot be replaced by another company. This will result in a patent which will give us exclusive rights to this groundbreaking FDM technology. The progress for this 2-year project will be measured through these milestones. The first 9 months will be used to design the prototype for the fiber placement apparatus, and after that we will integrate that apparatus onto the FDM printer and test consistent functionality over the next 7 months. After that, we will use 2 months to test the specimen with or without fibers to ensure that there have been improvements in the transverse direction. The final 6 months will then be used to optimize all of the parameters, including fiber density, alignment, and adhesion, to ensure maximal mechanical performance.
The key objectives over the course of this 2-year project will be to develop a prototype which is capable of placing the silicon carbide fibers between the layers during the FDM printing process. We also aim to ensure that the apparatus can handle fiber alignment, cutting, and insertion without significantly increasing the production time. After 2 years, we aim to have developed a flexible and functional FDM printer which consistently prints isotropic components with improved transverse tensile strength. This modified instrument should be able to accommodate many polymer fiber combinations in order to fit internal and customer applications. In conclusion, we believe that this project is feasible within the 2-year timeframe and well worth the $375,000 budget. The incorporation of silicon carbide fibers will expand applications in aerospace, automotive, and medical industries by offering high-strength isotropic components. The potential to revolutionize FDM printing and compete with SLS in a $2 billion market makes this undeniably a high-impact investment for big FDM printing. Thank you all so much for listening to our project proposal. If you have any questions, feel free to reach out to me or Amanda using the emails shown on the screen.